Okay, so actuator circuits. So function and testing. So an actuator is a load. So if we envision a series circuit, and most actuators are in a series circuit, there's a few parallel circuit options that we have where we turn multiple actuators on at the same time. And that's with some old fuel injection systems, but most actuators are in a series circuit. And they're the load for the circuit. So that means I have to have a power supply, conductors, and the actuator is my load. And so then really the big thing about actuators, because you're going to see we only have a couple of them, the big thing about actuators is how we control them, how we turn them on and off. Because you remember, a computer is digital. It's either on or off. Well, what if I want something on only halfway or a quarter of a way? How do I do that with a computer that can only turn something on and off? And I'm going to explain exactly the different ways we do that. So most actuators are either solenoids, relays, or motors. Those are the most common actuators we have. We could argue that the light bulb is also an actuator for the check engine light because the computer turns it on. It's turning something on. So we could argue a light bulb back and forth whether it's truly an actuator or not, but it kind of gives you an idea. All require two electrical connections, power and ground. Most rely on the principle of electromagnetism. So our solenoid, relay, and motors all work on electromagnetism. By understanding how these work electrically, we can understand their operation, properly test them, regardless of what name they're given. So this is really kind of a huge concept. So we're not down to naming. We're down to what is it? Is it a solenoid? Is it a motor? Is it a relay? Is it a light bulb? Because really, if I'm testing it, I'm not going to pull it off on the bench or take it off the car and test it. I'm going to test it when it's in a complete circuit, just like I would a light bulb, right? I'm going to check, do I have power and ground? If I have power and ground, the light bulb doesn't light up, we're going, the light bulb's bad. Same token, if it's a motor and it has power and ground and the motor doesn't go around, it's a bad motor. So we want to test things in a complete circuit, and that's pretty easy when I have a switch that I can just turn on and then I can test to see if I have voltage. It gets more complicated if we're only going to turn something on for 1 millisecond. Because now I need to do all those tests in 1 millisecond. Wait a minute, 1 millisecond, my meter takes 200 milliseconds to update. How am I going to do this? Obviously, we're not going to use a meter. We're going to use a scope, because a scope, I can see that change over time on very fast signals. Ohm's law applies whether that circuit is connected and current is flowing for 1 millisecond or for 1 hour. It doesn't matter. Ohm's law still applies. So it allows me to use Ohm's law to do diagnostics on very short periods of time. So although the circuits may look identical, there are several types of output signals from the PCM to control actuators. So any actuator is going to be connected to either power or ground, and the other wire of the actuator is going to be connected to a module. So some modules control the ground side, which is by far the most common. So the most common is we supply power to the actuator and the computer controls the ground. We call that low side control or ground side control. Some manufacturers like high side control. So they apply ground to the actuator all the time and turn the power on and off for the computer. What we're seeing now, modern vehicles, the last 10 years, we're seeing manufacturers more and more control the power and the ground going to an actuator. So they're both going back to the module. And we see this for fuel injectors. We see this for some other devices where the computer is controlling the power and the ground. And really, the excuse they give is so they can better monitor current flow. Well, if current's the same everywhere in a series circuit, why do I need both ends of the circuit? So the reason they're giving me, I'm having a hard time reconciling with my knowledge of testing and Ohm's law. So I'm telling you what I'm being told, not what I believe. So there's all now some manufacturers like injectors I've actually seen where they use separate switches on the high side and the low side, and they'll toggle them differently to do some really cool stuff on some diesel injectors and some other stuff. So they do some really crazy stuff. But being able to measure current, I'm just not buying that. To control current flow and protect the module better, that I would buy, because now I'm controlling the ground, I'm controlling the complete circuit. So even if there's a short, I can't flow too much through the circuit because I'm controlling how much current I'm putting on the circuit. That I completely buy, and I think that's why they're doing it, because it's a lot more expensive to do. So I think it's more about, protecting the system durability and control than it is about measuring current. Now, the byproduct of that is because of all that control, they are able to measure current. So we see a lot more data PIDs on a scan tool for current now than we used to, because the computers are seeing that, where before they just saw voltage. But I think that's a byproduct of the technology, not the reason for it. So the 4 types of signal controls that I'm going to talk about are simple on-off switch type signal, which is what we've been studying this whole time. Just like the light switch in your house, it's on or it's off. We're going to talk about frequency control. We're going to talk about duty cycle. And we're going to talk about pulse width modulation. And we're going to talk about the difference, especially between duty cycle and pulse width modulation, because manufacturers lie to us. They tell us they pulse width modulate things that they're actually duty cycling. So many times the engineers or the people that write the books use the wrong description for the type of control they're using. And that makes a real difference when we're testing, because the pattern on a lab scope is completely different. The theory of control is completely different. So that's something that we want to look at a little bit, and that is something I'm going to go over the difference. But let's start with a simple on-off circuit, because everything builds on top of this. So in this case, I have a fuse, I have a solenoid, goes to a computer at pin 35 and goes inside to a transistor, which is my switch. So with the circuit in its current position, what voltage would I see at pin 35?
You should see battery voltage potential, right?
Absolutely. I should see system voltage potential, because I have system voltage. It's gone through the resistor all the way here, all the way to an open circuit. In an open circuit, I can't use any of that potential. So therefore, I would see system voltage on my meter here. When this switch closes, what's going to happen to my meter reading? If I have system voltage with it open, what's it going to do when it closes?
The solenoid will work. EGR solenoid.
Yeah, well, it's not about the EGR. What is the voltage going to be at pin 35 when the switch closes?
It should be 0, right?
Should be 0, right? So I'm going to go between 12 volts when I'm off, or system voltage when I'm off, to 0 volts when I'm on, because it's ground side controlled. So the only time it's turned on is when that wire between B and pin 35 is grounded, right? So this is what my switched ground in the circuit right here. So I could test for that at pin 35, or I could test for it at B, couldn't I? Yes. So if I took a meter and went from pin A to pin B, I would see 0 volts until the computer turns on the solenoid. Then I'd see 12 volts, wouldn't I?
Okay, yeah.
Right. And if I see 12 volts, but the little solenoid doesn't go click or doesn't do anything, is it safe to say the solenoid's bad at that point?
Yes.
Okay.
Yes.
So you see where, I mean, we're kind of walking through the process. So EGR might be simple. I might be able to just command it on and tell it to stay on, and then I can test it. Or most manufacturers duty cycle the EGR, but they may have a command in the scan tool where I can turn it on using the scan tool. So a lot of times we do these tests in conjunction with a tool that I can talk to the vehicle's computer and say, hey, can you turn this on 100% so I can test it? So I can't do that with all my actuators, but I can do that with some, depending on the manufacturer, depending on the scan tool. If I don't have option for that, then I would need to test this under conditions that the computer would turn the EGR on. So now I need to understand how the EGR system works. And what I can tell you is we use it at light throttle on a warm engine. So I would need to test it going down the road at a light throttle on a warm engine. So should I put someone under the hood with the meter to test it when it comes on? And we'll go for a drive? Probably not the best option. So I probably want to use some longer leads that might allow me to cut back probe at the A and B connector and bring those leads into the passenger compartment with me. And then I could look at a meter and do that. But if I'm looking at the meter looking for something to happen, it's kind of hard to drive, isn't it? Again, probably not the best idea. So why don't I replace the meter with a scope? Because a scope's going to tell me if it goes high and low, doesn't it?
Mm-hmm.
That I could prove that the circuit is working electrically. So on a scope, if I'm looking at the B wire or pin 35, so I have my scope connected right here at B, because we know what A is. A is battery power, right? I mean, that should be there. So what I'm really looking for, I'm going to hook my scope to the side that has change. And I can see when it's off, I have 12 volts. When the computer commands it on, I have 0 volts. When it turns it back off, it'll go back to 12 volts. So again, a very distinct signal between on and off, isn't it?
Yes.
So, and then from here, is on really 0 volts or is it down at 1 volt? Well, 1 volt means that I have a volt loss, right? Or 2 volts means that I have a bad ground or bad computer ground or bad computer. If my off is, high, I'm not going to know if I have resistance on the power side without using another channel, look at the power and looking for voltage drop there. But when we're looking at simple on and off, this is it, simple on and off. And a lot of people have a hard time when they see this because, wait a minute, you have power when it's off, but nothing when it's on. Well, that's because we're on the ground side of the circuit. We're on the control side, when in this case, we're controlling ground. If this was a high side controlled, where the device is getting ground all the time and the computer is adding power, it would be just the opposite of this. Off we would see ground, and on we would see power because the computer's applying the power. Very few manufacturers do that. Honda and Chrysler both do. They like high side control. Other manufacturers will do it on occasion, but Chrysler and Honda are both known for it. But most manufacturers, we're going to see, power on the control wire off and then ground when it's on. So this is simple on and off. So we do have some circuits out there like that. Even as we move into these more advanced controls, this principle of voltage off and ground on is consistent throughout all 4 ways of control, because everything I'm going to show you is a ground side controlled circuit, because overwhelmingly that's how we do it probably 90% of the time. I mean, it is overwhelmingly the most popular way to do it. If it's high side controlled, everything's flipped. So the next thing we're looking at is frequency. So frequency is measured in hertz, and it's the amount of time a pattern repeats in 1 second. And frequency is measured from the beginning of a pattern to the beginning of the next pattern. So this is how we measure it. So in this case, in this frequency, it spends half its time on, half its time off. And if I just turn this on at 50%, we're going to do this, but now it's the frequency. So if I speed up that frequency, I'm going to condense that and make it more on. If I lower the frequency, it's going to be more off. So even though I'm not changing the amount of time on versus the amount of time off, I'm going to change how many times I do it in a second. So for example, if I do this once a second, 1 hertz, I'm going to apply power for half a second and turn power off for half a second. So as I build electromagnetic field, it's going to have time to pretty much fully collapse before I build it again. So that plunger in there is not going to go up necessarily all the way and stay there, or it's going to go up and down, up and down. It's going to cycle up and down, because it has time to rise and it has time to drop because we're only doing it once. What if I do it 100 times a second? Now I'm not allowing time for that electromagnetic field to collapse, and the level of that plunger is going to stay high. It's never going to come back down to the bottom, because every time it tries to collapse the field and drop the plunger, it's going to get pulled back up. So it's going to spend more time high. So with frequency control, it is basically the more times I turn it on and off in a second, the more time it's going to physically spend on. Everyone kind of following the logic there?
Yeah.
So frequency is defined by how many times a pattern repeats within what period of time?
Millisecond.
Not a millisecond.
Second.
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 So when we see the term hertz, that's what hertz is. So for example, in our house, the electricity that is powering up my lights and powering up my computer cycles at 60 hertz. That means the AC pattern repeats 60 times a second.
Yes.
Now, if I go to Europe, it only repeats 50 times a second
50 seconds.
because their system is higher voltage and 50 hertz, different system. So hertz, and that's why I want you to know it's per second, because this is important to where if I ever throw a scope on it and I want to know what the repeat factor is or what the frequency is, that's how we calculate it. But it also kind of shows you that change. I got to have a standard time base for that frequency to change up and down. And that happens to be seconds, even though I may measure it in milliseconds. I may measure what's going on, extrapolate that out, or look at the pattern in very small amounts of time. The actual definition is defined by a second.
Okay. Oh, sorry. Would you mind showing the
What's
previous?
that?
Would you mind showing the previous PowerPoint?
Oh, no, not at all. Let me do that.
So I can kind of see that mentally.
Yeah. So here is a
Okay, I see it.
pattern, and it's the pattern, the repeat on a pattern. It doesn't matter whether it's an AC pattern or a DC pattern. We can pick any point. So it doesn't matter. Here I'm picking the point where it rises to the point where it rises. I could just as easily pick the point where it falls to the point where it falls. I just have to pick the same point and look for where in the pattern it repeats back to that point.
Okay.
And then we're going to see how many times does it do that in a second. So it doesn't matter if it's an AC waveform where it's doing this, or a DC control pattern like this, where it's a digital signal. You know, on a waveform is going to be when the waveform comes back up to the first place it started. And we kind of saw that when we were looking at alternators, look at some other things where we had the AC pattern, or even wheel speed sensors. I talked about it with wheel speed sensors. So again, that's where that frequency. So some scan tools, if I'm looking at wheel speed sensors, may give me frequency, so I can watch the frequency change as I drive. I may have, if I don't have a lab scope, I may have a digital multimeter that measures frequency. So I could hook up to a wheel speed sensor and spin it and see if the frequency changes, which would at least give me an indication the sensor's generating a signal and it's a higher frequency the faster I spin the wheel. So there's another cheap way that I might be able to use a digital multimeter if I have a higher end one that does frequency, and actually test something that I should really have a scope for, but I don't, but I could hook it up and see, does it make a frequency? Does the frequency change? So I could test a permanent magnet sensor that way with a meter on frequency, because we know with what the frequency changes with speed.
Okay. Okay, thank you.
You bet. So duty cycle. Duty cycle is a measurement of on time of an actuator versus the amount of time it is turned off, and it's measured in percentage. So 100% means that it's turned on all the time, and 0% means it's not turned on at all. So normally we'll never see 100%. And normally, although some systems you may see 0, many systems we see about 5%, even when we don't want anything to happen, which is especially true of like variable valve timing and some other systems. So we may get down to 0%, but it's very rare we get to 100% because we still need to have this consistent frequency. So duty cycle is done at a fixed frequency. Once I go to 100%, I no longer have a frequency. I just have a flat line. So even at 100%, we're really at 99.5 or whatever, or however high it goes up, because it has to cycle to keep that same frequency. That's also why we don't really see zero very often, although occasionally you do see things go to zero, which is completely offline. Then it goes into control. But we don't see solid up all the time. So a duty cycle is a measurement in which of the following scales? Percentage. Okay. So I'm going to show you how this works right here. So I have two scope patterns here. And each of these scope patterns, I have taken a measurement and I've used what are called cursors. So you can see number 1 and number 2. These are my cursors. My delta time is the time in milliseconds between my two cursors. And I can see I've got 1, 2, 3, 4 divisions separating my two cursors, which means each division has to be 20 milliseconds. So this is my pattern. It drops here, comes up, then it drops here. So this is one cycle, and I'm going to do this at a certain amount of hertz. Now the hertz I'm seeing right here, frequency 12.5 hertz. So with where my cursors are at 80 milliseconds, I can repeat that 12.5 times in 1 second. That's where that 12.5 hertz is coming from. Okay. So that is my whole pattern. Now, in this case, I have a 25% duty cycle because I'm turned on for 25% of the time. And that's what we did here is we moved the cursors over and showed 20 milliseconds. Or 20 milliseconds is 1/4 of 80. So my whole cycle is 80 milliseconds in this case. 20 milliseconds is turned on, 80 milliseconds is turned off. This would be a 25% duty cycle. If it was on for 40 milliseconds and off for 40 milliseconds, it would be 50% duty cycle. If it was down low for 75 milliseconds and then up high for for 60 milliseconds and up high for 20, that would be 75% duty cycle because it would be turned on 75% of the time. So what this allows us to do is say I have a solenoid with a plunger in it. If I only have a 5% duty cycle, we're only energizing it 5% of the time. So I'm going to get a little bit of lift, right? Because I'm doing it very quickly. So I'm going to come very quick. If I get to 50% duty cycle, now I'm going to be about in the middle, 75%, 3/4 up. So I can change the opening of something that's linear with a digital signal. So basically, because this is happening so fast, what it does is it divides our applied voltage by the duty cycle. So in this example, I have 25% duty cycle. If I apply 12 volts, I'm effectively going to see 3 volts at my actuator. 50% duty cycle, 6 volts. 75% duty cycle, 9 volts. So you see that by using the duty cycle, I'm actually instead of having a dial to dial up and down the voltage, we're giving it full voltage, but for only short periods of time. So it's effective voltage. And if I put a meter on it, because meters are so slow, I would literally see 3 volts, 6 volts, 9 volts as I change the duty cycle.
So is it
literally
so
what's that?
So is it the actuator that it's allowing this to go forward like this? It's already set in motion.
No, so what we're seeing here is the control signal from the computer. So the transistor in the computer is holding it down in this case for 20 milliseconds and letting it up for 60 milliseconds, holding it down for 20. So my actuator is just a load. It's just the load in the circuit. Many actuators work on electromagnetism, and it takes time for the electromagnetic field to collapse, which allows it to kind of pull it up and hold it at a certain level. And basically, and if I used a voltmeter, I would see you know, 25% of the applied voltage in this particular example, because it's cycling so fast. I would only see it divides the voltage by the percentage. So, but this is
But the
all done
scope,
by the control module.
So
but
what's
a
control?
scope would show you all the way to 12 and back to 0.
That's
in a
what we're
short
looking
time
at right
period.
here, is all the way to
Yeah.
12 and back to 0. Yep.
Huh.
You just don't see a voltage scale on the side here. And I'm not sure the scale used, but yeah, that's what we're looking at here. So this is all the way from 0 to voltage. We got some captures that are coming up, and as we get into other systems where you'll see this, and we're doing engines next. I've got stuff in variable valve timing where you'll see the duty cycle concept. So at this point, I'm really more about the concept of it, so you know what duty cycle is. By the end of the class, you're going to have seen a lot of pictures on, because I use it to describe different systems, whether we're looking, you know, at EGR, whether I'm looking at variable valve timing, you know, anything we're using that duty cycle control with. I have a lot of scope patterns that I pull up to show, here's where the computer's turning on, here's what we're doing, here's how it affects other things, so we can see the relationships.
The name duty cycle is just a little off-putting because to me, in my mind, it would seem like duty cycle would be on time, but
Right. Well, and it would, but there's a reason why we don't do that. Because, so I could say it's a 25% on time, and that would be, you know, okay. And you will see it referred to that way. But the reason why we shy away from actually using the term on time for duty cycle control is because this time varies based on the frequency. So in this case, this is a 12.5 hertz signal. But if it's 25 hertz, twice as fast of a signal, then a 25% duty cycle would only be 10 milliseconds, different amount of time.
okay.
So yeah, we can talk about it as far as a percentage of on time, right? And we do hear it used that way, indicating that it's only turned on for that percentage. But that's why we measured in percentage, and our scan tool PIDs will show the percentage. And another reason for that is our last type of control, which is pulse width modulation, is actually measured in on time. Because unlike duty cycle that has a fixed frequency, so with duty cycle, my frequency never changes. With pulse width modulation, not only do we change the amount of time we're turning the actuator on, we're also changing the frequency that we do it. So fuel injectors, for example, are pulse width modulated, because I need to change how much fuel I'm putting in the engine, whether I'm at idle or whether my foot is to the floor and I'm trying to get on the freeway. Different amount of fuel, so I need to hold the injector open longer to allow different amounts of fuel in. Also, my engine, if it's going around at 800 revolutions a minute, I'm going to fire the fuel injector 400 times a minute, or once a cycle. It takes 2 revolutions for 1 cycle. So that's at idle. Now I'm trying to get on the freeway and my engine is doing 4,000 revolutions a minute. That means now I need to turn that injector on 2,000 times a minute. That's a different frequency. So that's why I use injectors to kind of explain the pulse width modulation, and we do pulse width modulate injectors. But it's because I have to be able to change when I do it as well as how much I do it. Other systems in the car are not necessarily speed dependent. So I can duty cycle them. And obviously to duty cycle something requires less computing power, i.e. cheaper than pulse width modulation. A lot of times manufacturers will say they pulse width modulate something when in fact they duty cycle control it. And as soon as you put it on a scope, you can see it. Sometimes that's a distinction without a difference. Other times it's, you know, but it's huge if you're going deep to diagnose something or kind of trying to understand what's going on sometimes. So pulse refers to turning an actuator on and off. Width refers to the amount of time the actuator is on. Modulation refers to the fact that the actuator is being controlled or modulated over a period of time at different frequencies. Pulse width modulation is different from duty cycle in that both frequency and on time varies. With duty cycle control, the signal frequency never changes. That is the takeaway here. That is the defining difference between the two. So as I look at pulse width modulation, you can see, we look a little bit different. I got my flat line here where I'm off. And right here is where I turned it on. So in this case, I turned it on for about, 6.5 milliseconds. And that is the width of the pulse. This spike here is an inductive kick. So if I generate an electromagnetic field, there's a lot of energy. That energy needs to go somewhere. So many solenoids, if there's not a Zener diode or something else there, we're going to see an inductive kick back on the line. And that's very common. So this happens to be a fuel injector right here. And fuel injectors all have inductive kicks. Ignition coils have inductive kicks. So the bigger the electromagnetic field, the more likely we're going to see an inductive kick on the pattern. And I mean, if this right here is my system voltage of 14 volts, we got like 60 volts here. Okay, so ignition systems, 12-volt ignition systems will get inductive kicks of over 200 volts. So I can get, so when we say 12-volt system, well, it's more like our system voltage. It kind of varies. Now, granted, this is happening for a very, very short period of time. But that's why, computers and modules have to have a certain amount of hardening in them, a certain amount of protection. So in this example that I put in the PowerPoint, it's the same example I already used. The fuel injector is turned on once per engine cycle. However, as the engine's RPM increases, so does the frequency of turning the injector on and off. In the following illustration, the injector is turned on for 6.85 milliseconds. So that's pretty close to 6.85. And we're using the cursors, which I can bring in to measure something on my scope. So even though my scope doesn't have that digital number that my digital multimeter has, I could take a pattern, freeze it, bring the cursors in and get my digital number. And depending on the cursors, these ones here are just showing time. Many cursors give you both time and voltage at the same time. Some scopes have different cursors for voltage and different cursors for time. So it just depends on how the scope is configured. Pulse width modulation is measured in which of the following?
On time.
On time, you got it. And so we will see that in seconds. So unlike percentage, we're going to see this in actual time. So that's why I think we don't hear on time for duty cycle. Although we might hear someone say a 25% on time, we still have that percentage there. Where when we talk about here, on time is the only way we measure it, and it's a direct time measurement. So many times they don't say on time with duty cycle because it's assumed. If I have a 25% duty cycle, we know we're turning it on 25% of the time, so it would be redundant.
Gotcha.
In duty cycle, frequency never changes, but pulse width modulation, it does. Is that true?
True.
True.
True. Okay. So actuator power normally comes from 12 volts. So almost all actuators from all manufacturers work on 12 volts. There's very few exceptions. I mean, I can think of one, put it that way. And it happens to be on a Dodge diesel. So pretty much universally, these work on 12 volts. Now, in this example, we're ground side controlled. And I know that because power is going to all three of these. And I obviously don't want to turn all these on at the same time and for the same amount of time. So therefore, any wire they're sharing, whether it's power or ground, has to be their common, which means the computer is going to control the other side of the circuit. So if I'm not sure if I'm working on a power side or a ground side controlled system, all I got to do is find the actuator and trace the wires. if one wire goes to the battery like it does here, it has to be ground side controlled. But if this was chassis ground here, that would mean it'd have to be high side controlled. So the computer has to control the opposite of whatever the other wire is going to. And that wire is either going to go to power and ground, most likely power. So as I look here, I've got my digital multimeter and I can see 12 volts on the supply side. I should have the same 12 volts in all of these. And we're going to pulse it. And if I was close to a 40% duty cycle, I'd see around 5.5 volts. When we turn it off, we would see 12 volts. So key on engine off, for example, I'm going to see 12 volts on both sides of my actuator. With the engine running, I can see that, hey, something happened. Is it the right amount? I don't know, but I no longer have system voltage, so I know the computer's turning it on and off. So whether this reads 9 volts or 3 volts is really immaterial unless I have a scan to where I can compare duty cycle to and that kind of things. Here it's an injector, so it's pulse width modulated. I'm just looking, does the voltage move at all, right? Is something happening here? Because this is the only tool I have. On the other hand, I could use a scope, hit the same test point, gives me a lot more information. I can see I'm going ground, I have power. We just grounded it with the computer. We released it, got my inductive kick, we're back down to vehicle power, and we're going to turn it on again next time. And I can see exactly how long it's turned on for. I can see if how long it's turned on for changes based on engine RPM. So you can see the connection between using a scope or a multimeter is the exact same. The difference is how much information do you want? And a lot of people like a meter because, oh, it's simpler, the scope is confusing. Well, is it really simpler if you're not getting good information?
No.
Right? And that's why I'm such a big fan of scopes, because I know that's how we fix cars and that's how we understand circuits. And until I got good with a scope, I really wasn't good at diagnosing electrical circuits and understanding how they work. Those two things went hand in hand. So now that we've talked about how we control actuators, let's look at some different actuators. Although most actuators can be controlled by any of the previous mentioned strategies, the actuators themselves are very different from each other in function. Let's look at some of these in order to determine which category of control different actuators might fall into. So an electric motor. So electric motors use the push-pull effects, the magnet to rotate the motor shaft. We've already learned about motors, right? We learned about our DC motor with starters. DC motor is a DC motor, or we're not going to spend an hour talking about it again. You know, a motor is a motor is a motor as far as the DC motor goes. Now, some are brushless, some are not brushless, but they're all working electromagnetism. And since we're not rebuilding them, we really don't care because all I need to make them work is a power and a ground. So my motor will rotate a little bit, or I can get it rotating a lot, maybe. Oops, doggone it. There we go. Now I got it rotating a lot. So motors, we have our commutator, brushes, unless it's a brush type motor, my armature, and permanent magnets. So if I look at my little radiator fan here, I can see I've got power and I've got ground. If I put a switch in here, or if I replace this ground with a computer, say this is my radiator fan, that's probably going to be a simple on-off signal, isn't it? Either I want the fan on or I want the fan off. Is that a pretty good guess? Okay. Now, if it's a fuel pump, in the old days, we would just turn it on or off. Now we tend to duty cycle our fuel pumps because I want greater control of the fuel pressure. So in the old days, we just used to turn our pump on, let it run full speed, and we would just dump back the fuel we didn't need. So my pump's sitting there running at full speed all the time. Well, why don't I get, if I only need 25% of the fuel, why don't I only run my pump at 25% of the speed? So in order to do that, I need to start looking at what? Duty cycle. Now I can slow the pump down and speed the pump up, which is going to what? Create less wear and tear on the pump, so that pump's probably going to last longer. And I'm using less electricity, so that's less electricity I need to generate from my charging system to put back in the battery, better fuel economy.
Yeah, it's more efficient.
And yeah, we care about that little bit. Another type of motor is a stepper motor. These are similar to a DC motor. However, the stepper motor is much more precise. About the only place we really use these is the idle air control motor before the early 2000s when we went to drive-by-wire, 2003 to 2005. And these literally walk their way out and walk their way back in. And many times we'll see the display in counts. So what these normally do is when you shut the car off, it goes all the way down and it counts its way out from all the way down. You start the car, now it knows now how many counts it is away from being completely closed. Next time you shut the car off, it goes down and recalibrates. That way, as you get dirt or other things in there, it's constantly able to adjust its calibration. So very, very precise motor. Again, digital control. They're controlling both the high side and low side here so they can reverse the motor, right? Because if I want to lower the idle speed, I need to move it this way. But if I want to move the idle speed bigger, I need to move it this way. So I need to constantly be able to go both directions. That's why you see the wires going back to both. So this is actually two motors in here, not one. And here's a picture of it for those of you that are not familiar. This one happens to be a GM, 4 wires going to it, 2 separate circuits. Here's the little cone that goes in and seats to seal off the air. And it backs off in order to allow air to go through it. And this is how we controlled idle speed for a number of years before we went to drive-by-wire technology. So again, duty cycle control here. I don't want it all the way in or all the way out. I need it somewhere in the middle. So these are duty cycle controlled. What is a solenoid? A solenoid, we learned about these with our starter solenoid, but let's back it up a little bit and oversimplify it. A solenoid is something that generates an electromagnetic field around an iron core, causing the iron core to move. That's it. The only question is, what do we want to have happen when we move the iron core? On the starter, we spent some time talking about how it moves back, makes the electrical contact, as well as it pulls the Bendix gear out for the overrunning clutch to engage the flywheel. So it does a couple of things on a starter when we make that physical movement. But we're not limited to trying to start a vehicle. Common examples of solenoids would be our fuel injectors. They're a solenoid. An exhaust gas recirculation valve, a solenoid. Again, I have a metal plunger in the middle. I want it to go up and down. That's a solenoid. Transmission control. So here we're controlling pressure. We also control how we shift. So I can control the amount of pressure by slowly moving this in and out. So these are normally pulse width modulated on transmission pressure control solenoids. The shift solenoids are normally either on, off, or duty cycle controlled. EGR is normally duty cycle controlled. Fuel injectors are pulse width modulated. So here I have different types of solenoids doing different physical things. We even control them differently electrically. We use all 4 different types of electrical control on solenoids. But they're doing different things. But is really testing them any different? It's a solenoid. Got a power, got a ground. Does it go click when it gets power and ground? It should, because we know that that metal thing's supposed to move inside. If I give it power and ground and it doesn't go click and nothing happens, are we pretty good that it's bad?
Yes.
So I can spend a lot of time looking up specifications and resistance specifications, other things that probably aren't going to help me fix the car much. Or I can just know it's a solenoid, and if it gets power and ground, it's supposed to go click. It should move. And now in the case of transmission solenoids or EGR solenoids, I can actually watch it jump up and down or move in and out. Injectors, all I can really do is hear them click. So here's a fuel injector, again, a solenoid. In this example, the ground side of the fuel injector being controlled by the PCM. And so every time it energizes the electromagnetic field, the plunger comes up and fuel is going to come into the engine. When it collapses the field, the plunger goes down and stops fuel flow into the engine. It's a solenoid. You know, the only difference it is really between your starter solenoid and these solenoids is the starter solenoid has two sets of windings, a pull-in winding and a hold-in winding. These all only have one set of windings. Here's an example of a couple more injectors. Injectors are always pulse width modulated. And we can see here, this is an older throttle body injection system. Here's a multi-port injector right here where we have one injector for each cylinder. You can see the two electrical connections right here, two electrical connections right here. One's going to be power, one's going to be ground. And the computer on injectors, I can't think of any one on gasoline engines where the computer does not control the ground side of the injector. So power is supplied by a common power source. Power goes to all the injectors, and then the computer controls the ground to each injector separately. So if we look at a good injector pattern right here, I zoom this up. Here I have a 0 to 20 millisecond scale, and I have 0 to 100 volts. I'm on the 100 volt scale. So that's why this is so low. This is my system voltage. Right here, we commanded the injector on. And right here is where we commanded the injector off. So this is what we would call our pulse width. So I can tell by this pattern that electrically it's good. I have a spike, so I was able to generate an electromagnetic field. Because if I didn't have a spike, that would mean that I had a short injector because no electromagnetic field was generated. So I know I don't have a short injector, and I know that the computer commanded it on and the electrical circuit's working. I don't know if the injector actually opened up and sprayed fuel because it could be plugged, it could be stuck. I mean, there's other things that can happen. But electrically, I know that the circuit is working correctly.
Spike looks like less than 20 milliseconds.
Well, the whole scale is only 20 milliseconds from here to here. That's 20. You got 4, 8, 12, 16, 20. There's 20 across there. We only turned it on for what looks to be about 4 milliseconds. I'd have to grab the cursors or focus my glasses, but that looks like about 4 milliseconds. Pretty close. So if I change the scale, say I went to a 100 millisecond scale going across, this would look very skinny. It'd be very small, and I'd probably see other firings, but it'd still be the same amount of time. Just how the picture is painted would look different. So relays. A relay is an electromechanical device that utilizes a small amount of current to energize electromagnetic that closes the contacts in a circuit carrying a higher amount of current. So in this case, we can see I have a fuel pump, an AC clutch, and a cooling fan motor. I have my computer right here. I have power that's coming down, goes to the computer, and it goes to all three relays. And I also have power coming down here, which feeds power on this side of the relay. So I have power here and I have power here. So the computer, obviously, since this is a load, computer has to apply a ground. When it applies a ground, it's going to pull this switch closed for this circuit and turn the fuel pump on. So a relay is a load for one circuit and a switch for another circuit.
Hmm.
2 circuits in a relay minimum. There's a switch circuit and a load circuit. So if we look at our relay here, and this happens to be a 5-pin relay. Many relays only have 4 pins. If it has 5 pins, that means there's a normally closed contact, which would be pin 87A. There's pin 87. Power in is pin 30, and then there's 85 and 86. So 85 and 86, which is circuit 1, are the load circuit. Circuit 30 and 87 are the switch circuit. So we can see here, when I energize this electromagnetic field, we're going to pull the arm, we're going to pull this down. When we pull this down, we now are going to come in contact with a normally open contact. So most relays do not have this blue, do not have this other part. All they have is the red. And the reason for that is the original relays all kind of came 5-pin, but most circuits didn't use this blue part here for the normally closed contact. So then they came out and made a cheaper 4-pin relay, and they made, now there's several different kinds of relays and some solid state ones. But 87A is the default. So there's times, just like when we did that blower motor drawing exercise, when the relay wasn't energized, the blower motor signal went through here, but as soon as we energized the relay for high, boom, this switched, and now we're feeding the power through here. So it just, we're able to change circuit. We have circuits that might be a default position on, and we only want a signal to turn it off. You know, so that, you know, there's something else that we, you know, do. So, you know, a lot of different wiring options with these. Very universal. Bosch invented them, and everyone used the same one for a long time. Now we see, you know, different configurations, but the principle is the same. So here is a standard Bosch relay. You can see the pins on here. This is standard, and 86 and 85 are my control. 30 is my power in. 87B is my normally closed, and 87 is my normally open. So when the relay is energized, when I get power and ground here, power will flow from here to here, or from 30 to 87. And you can see it's in the default position right here. And we can have a little diode right here, so we do not get the electromagnetic spike back, the inductive kick. So here's our relay in operation. I just did a 4-pin here. So I've got 85 and 86, which is my control circuit for the load. And then I have 30, which is power. And pin 87 is going to go to my fuel pump or my AC compressor or whatever I want to turn on. So when I generate an electromagnetic field, we pull this down. We've now made electrical contact. So now power is going to come through here, all the way through here, and out there. When I de-energize it, it opens up, and it's spring loaded to open up.
Oh.
So that is our relay operation: on, off, on.
The only difference between that and then the 5-pin, it has the 87A that could be energized with the switch open. Is that the idea?
Yeah. So the
If there's something
87A,
connected to it?
right? The 87A would come off the top here. There'd be another set of contacts, and it would go over. So I'll back up. Yeah. So 87A is the blue, and it comes up over to here.
Now, why would you said most don't come with that blue, but why would they add that?
Well, that was originally there, and we use it like on cooling fan circuits where we want to switch between series and parallel. We use it for other circuits where we want to push up, or it may be something that I want as a normal condition. So say I have a car that I want to, shift between a normal operation and a special operation. I might use a relay to switch those functions. I could use this in combination with a dimmer switch, for example. Maybe this is my normal low beam, and we're going to energize this relay when I want high beam, and then pull this down, and then high beam comes out here, but low beam stays over here.
Okay.
Right? Because I'm not going to drive with my high beams on all the time. So I'm only going to use the relay to turn on the high beam. So I don't need as big a switch.
Okay.
And I use the relay to control it all the time. So I'm feeding power through here from my low beam all the time. And if I turn to high beam now, I'm going to energize the relay and I get high beam.
Okay.
So that would be one example when we might do that, where I have a default position that doesn't require any electrical power, and then a position I don't use as often that does require electrical power. So relays are cool. So a lot of times when you wire in accessories, whether it's lights or things like that, you should wire through a relay. So instead of putting a switch on the dash to turn the lights on directly, you should run smaller wires into the dash, control the relay, let the relay turn on the lights on and off. Like if you're putting off-road lights or driving lights or fog lights or something on. The other thing is, since I can control the relay with either power or ground, I could literally run ground from under my dash to a switch, run a ground wire out to a relay, power my relay underneath the hood. Now I don't have a wire going through my firewall that has power through it that might rub and cause a fire or cause a problem. So you can design things to make them much more resilient and safer using relays also. Also results in having to run less wires back and forth sometimes.
So can I ask a quick question?
Sure.
Thinking about this, if you're adding a relay to do something, if you're adding components to a vehicle, is it similar to adding to a house? Like if, are there, like, is there ever a time that you could kind of overload things?
Oh,
Put
absolutely.
components in, and if so, what would you use as like a breaker or to like a GCFI to kind of counter that so that you don't blow out components?
Okay. So we don't use a GFI on cars because we're DC instead of AC. But what I would do is I would run a fused circuit going to 30. I can also branch off that fused circuit and go over to 86 with it because I can feed power into both of these. I could run a wire from inside to ground off a toggle switch or whatever to turn it on, and then this is going to go out to my vehicle. So now I have a fused circuit that has a dedicated fuse going all the way back to the battery, so I'm not going to overload anything. On the other hand, if I didn't use a relay and I just said, you know what, I want to control it with just a switch, now I need to run a wire, which I could still fuse all the way into the car to a bigger switch, run that switch all the way back out to turn them on. So now I've got a lot more hot wires going. And since everything is surrounded by metal, that's more things that could rub through arc and blow the fuse. A lot of times though, I need to control some of these things with an existing switch. So for example, my running lights, my driving lights, by law can only come on with my high beams. So when I wired my driving lights, I took pin 86 and it is spliced into the wire going to my high beam headlights. So anytime my high beam headlights are on, there is power at pin 86. Pin 85 is the ground for that load then. So pin 85 goes back to a switch on the dash that turns the ground on and off. Because just because I have my high beams on doesn't mean I want driving lights. So I need two ways of controlling this. I need to be able to turn them on and off when I want them, but not allow them to be on if the high beams aren't on. So therefore I let the high beams control one side of the load and my manual switch control the other side. So that's how I control this. This is getting power straight from out of the basic in front of the battery through a fuse circuit. And then this is going to go down to my lights. But that's how I'm able to. So now I don't need to worry about burning out my headlight switch or burning out the wires going to the headlights because this is a very small load.
So
If
it
I just
redistributes.
spliced into the wire going to the high beam headlights so the driving lights came on every time, or wired them in where I went through a switch to turn them on, now I'm going to overload probably my dimmer switch and my headlight switch and burn them both out.
So if you use the fuse, that kind of redistributes the.
Yeah. So what I'm doing is
How-
I'm running a branch circuit. So it'd be like if I was in a house and I have a kitchen and my house is old and there's only one circuit and all the outlets in the kitchen. I really want to be able to run my microwave and my coffee maker at the same time. And I like a toaster also. And I can't do that with that one circuit. So what we would do is we would go all the way back to the panel,
Right.
grab another circuit, and we would have to run it from the panel at the house all the way to the kitchen, drop it down the wall, and put a new receptacle in there. So
Right.
now I have two circuits in the kitchen. Now I can run my microwave and my coffee maker at the same time because I can put them on two different circuits. So I'm still using the same amount of total power, but I now have two free ways to get there. And that's what we do on a car when we add fuses I have the ability of going all the way back to the battery or putting another distribution box in right off the battery or another fuse box right off the battery. And then I can, add more things because I'm not going to overwhelm my battery until I get really crazy with some super high-end stereo stuff, in which case we need a bigger charging system and a second battery. But for most stuff, all we're going to do is we're going to go back and we're going to pull another line up from the main, basically.
Okay. All right.
And is there a typical convention with, like you just described in the example you just gave, 86 being the power coming from the headlight high beam switch, 85 being the ground? Is that normally the case? 85 is the ground, or does it go back and forth?
Yeah, that's all DIN wiring, and unless I made a mistake, but my memory is 86 is power and 85 is ground.
Okay, just curious.
And some of them, it doesn't make a difference. You can run them either way. Other ones have a diode and they'll only work one way. But my memory on the DIN numbering is 86 is the power side and 85 is the ground side. Because circuit 30, circuit 87, circuit 87A are all in that DIN protocol.
I'm not familiar with what you're talking about.
We talked about it when we talked about schematics a little bit. That is the German numbering system. It's Deutsch.
Oh, now I remember. Yeah.
Yeah. And I just had the one page there and I think I went up to 30, but it goes all the way up. So 86, 85, all that stuff are all defined in that DIN. And that's kind of the neat thing about using the Bosch stuff is that it's all DIN numbers. So if you're not sure, you can just look up the DIN numbering and you know exactly what stuff's supposed to be. And there's some things that the Europeans do really well, and the DIN is one of them. But no, my memory is 86 is power, 85 is ground. Because circuit 30 is power and circuit 31, if I remember correctly, is ground. And you would think that the lower would always be the power and the upper would be the ground, and 85 and 86 are opposite of that. And that's how I remember it. Got to find a trick. But yeah, it is neat how you can control two different sides of the relay with two different switches, and they both need to be on for it to work. So it just allows you to do a lot of cool things. Or another example might be, I only have power going to 86 with the key on or with the engine running. So now as soon as I turn the engine off, it turns the relay off. And I control the ground for when I want it on off. So we can do a lot of different ways of doing this.
So it's kind of built-in redundancy.
Yeah. Like I said, relays are really, really neat. It's just really amazing what you can do with them, and circuits work so much better with them. But I think a lot of people are intimidated by them because they don't really understand what they do, how they can work, and how many different things we can do with them. And they're just like little magic things, and we use them on all kinds of circuits on cars. So the more comfortable you're with them, the more comfortable you're with understanding that one part is a switch circuit and one part's a load circuit. What what does it do? What is it supposed to have? And there's such a great test point because I divide a circuit. I divide the control side into two halves, and I can divide the load side into two halves. And so it really, I mean, the load and the switch side both into the two halves. So I can, the load, I can divide it. The switch, I can divide it. What do I have? So a relay contains a high and low circuit. Which of the following components does the high current circuit act like?
Number one, load.
Switch.
No, number two, the
Two.
switch.
Switch.
Two.
Switch. That's what.
Switch. The high current circuit is the switch in the relay. The low current circuit is the load in the relay. That's what allows us, because a relay pulls about 50 milliamps, not very much. So it's not going to adversely affect a circuit I've attached it to, because it just doesn't pull that much current. But I can switch 30 amps with 50 milliamps. That's huge. So it really allows me to use a very low current circuit to switch a high current circuit. And they have 50 amp relays also. So, I mean, you can switch a lot of current with a very small amount of current.
Okay.
So ignition coils. Ignition coils are another. What's that?
What was the answer?
Oh, number two, switch.
Switch.
Yep. So ignition coils. So ignition coils, and we're going to get into exactly how ignition coils work. But even if I wasn't comfortable with this, I got a wire right here, which is my power wire. I can know it has to be because this is my ground and this is a load. So when we energize this, we flow current through the coil. When we release it is actually when the coil fires the spark plug. But again, the load of the circuit of what we're looking at is the primary side of the coil between A and B. And so we're turning it on, turning it off. We're going to pulse width modulate this if we are controlling it directly by a computer, because the amount of dwell time or saturation time is going to change, and how often I do it has to change. So that's the definition of pulse width modulation. Changes frequency and changes the amount of on time. Lamps are another one. Like I said, we kind of threw that into where, yeah, it really technically is PCM commands the light on or off, or ABS commands the light on or off. So it is, could be called an actuator, and that's why I threw it in here. So again, most lamps have power applied to them and the computer controls the ground. Other lamps have ground applied to them and the computer controls the power. It's just about how the engineers design the circuit. But the light bulb is going to have one of those two things all the time, and the computer controls the other.
Resistor.
So actuators have two wires. Operation is controlled by the PCM based on sensor inputs. PCM can control power or ground to activate the actuator. Most actuators use the principle of electrical magnetism. Is that true or false?
True.
True.
When testing an actuator, the presence of voltage must be checked. True or false?
True.
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 Yeah. How else do I know if it works unless it gets voltage, right? All actuator control circuits use two wires.
You just
True.
said that, but
True.
what's throwing me is not all.
Yeah. All actuators use two wires. Now, one of my wires, maybe the engine block, but on some old solenoids and stuff like that. But yeah, this is one of the few things that's all. I need to have a power and a ground for the actuator to work.
Okay. Yeah, because I like two or three slides before this said it. It said it,
Right.
but I wasn't. It kind of threw me. I was.
Yeah, no, I'm not trying to trick everyone. I'm just putting these in here to really drive home the points.
Okay.
Actuators are always duty cycle controlled.
False.
False.
False. When testing an actuator that is pulse width modulated, the power probe should be used. True or false?
Wait a minute.
False.
Let me see that.
False.
False. Did I talk about a power probe in this presentation?
No.
Okay, so even if we were paying just a little attention, hopefully we were able to get there. When I throw something in that I didn't talk about and I say it should always be used, that's a good clue that that's false. So these are the review questions.